In this lecture, we will be discussing two important theorems, namely Thevenin's and Norton's theorem, which are two of the most basic theorems of network theory. Thevenin's theorem states that it is possible to simplify any linear circuit irrespective of how complex it is to an equivalent circuit with a single voltage source and a series resistance. Similarly, Norton's theorem states that it is possible to simplify any linear and bilateral circuit irrespective of how complex it is to an equivalent circuit with a single current source and a parallel resistance. In these two statements, the most important term is linear circuit. Here, I have already drawn a circuit for reference in which V1 and V2 are independent voltage source, R1, R2 and R3 are pure resistance, Z1 and Z2 are impedance, and 5I is dependent current source. Now assume that a question is provided to you in which you have to find three values of Z which needs to be placed across the terminals A and B so that the current passing through impedance Z is equal to I1, I2 and I3. Obviously, we will be getting three different values Z1, Z2, Z3 for the corresponding currents. But if you are going to solve the complete circuit 3 times, then it will take a lot of time. A far better way is to solve this question using Thevenin theorem, which states that any linear network like the one we have can be transformed into a single voltage source, which is the Thevenin voltage, and a resistance in series, which is the Thevenin resistance. After converting the original network into Thevenin equivalent circuit, we can connect the two ends of the circuit by the impedance Z and can find the value of Z1, Z2 and Z3, which will be much easier. Similarly, using Norton's theorem, we can convert the original network into a current source and a resistance in parallel to the current source. Here, we have to put the impedance Z across the ends of the resistor and can find the value of Z1, Z2 and Z3. Even though we are talking about the Thevenin and Norton's theorem, but at the end of the lecture, you will get to know that these theorems are not applicable in semiconductors, and the reason is highlighted in green color. That is, semiconductor devices are usually non-linear circuits. Now, we will learn about what are linear circuits as well as few other common types of circuits. In mathematics, you know that any straight line can be said to be linear graph, like these three straight lines which I have drawn just for having examples. However, when we come to topics like voltage-current relationship, there is a limitation, which is a graph will be said to be linear if it is a straight line and it has to pass through the origin. You can understand it in a very simple way. Assume that we have a graph like this. It says that a finite current is flowing through the device even when the potential difference is zero. But is it really possible that we have a device in which we have not applied any input, that is voltage in our case, and still getting the output current? It is practically not possible, as from the Ohm's law we have potential difference V equal to resistance R multiplied by current I. So, potential difference is directly proportional to current I. It means that when current is equal to 0, then the potential difference must also be 0, irrespective of the value of resistance R. I hope you will remember this point, that when we talk about linear graphs or voltage-current relationships, then the graph must pass through the origin. Another term which you studied in definition is bilateral. Bilateral simply means that suppose we have a graph which is similar in opposite quadrants, then it is bilateral. Otherwise, it is unilateral. Take this graph for example. This is a bilateral graph, but this graph is unilateral. Bidirectional and bilateral graphs are same thing. Similarly, unilateral and unidirectional graphs are same thing. Now, if you observe carefully, then you will notice that if a graph is linear, then the graph will be bidirectional also. However, the reverse need not be true. For example, take any linear graph like these two graphs. Both these graphs are linear as well as bidirectional. However, consider a graph like this. The graph is bidirectional, but it is not a linear graph. So, in the statement of Norton's theorem, the word bilateral does not have much significance as it is already included in linear property. We usually compare the word linear with a straight line. That's why after a while many students gets confused whether this graph is linear or not. However, when you will study signals and systems, then you will get to know another way to prove that this graph is not a linear graph. As I already told you that Thevenin's and Norton's theorem are generally not applicable on semiconductor devices as these devices are usually non-linear. Even though these theorems are not applicable, but still you should have clarity about the reason why these theorems are not applicable. By merely looking into the graph, one more property of an electrical device you can easily determine, which is whether the device is active or passive. If the current voltage graph remains in first or the third quadrant, then it will be considered as a passive device. However, if there is even a single point in the second or fourth quadrant, then it will be considered as active device. When you observe any graph, you can determine the power dissipated by the device, as power is given as potential difference multiplied by current. Now, if the graph is present in only first and third quadrant, then in both these cases the power dissipated will be positive. In the third quadrant also, two negative signs will cancel each other so that the answer will be positive. However, if the graph is present in second or fourth quadrant, then the power dissipated in the device will come out to be negative. This means that the electronic device or the circuit has the potential to supply power to the network and hence is called an active component. Even though Thevenin's and Norton's theorem are not applicable, but Kirchhoff's current law, Kirchhoff's voltage law, mesh analysis, nodal analysis, all these are applicable on semiconductor devices. Now, at the end, read few important points on your own. You can understand these points very easily.